We've already seen the electrophilic substitution mechanism. You saw it earlier where chlorine was used to replace hydrogen. Um, we'll look a little bit more in detail at the mechanism itself, though, for those of you writing the higher level exam. Okay, so remember, an electrophile is something that is most likely positively charged, so something that seeks negative charge. Now, even though benzene, we can represent it with 3 double bonds, all right, it has lots of electron density, but none of these double bonds will undergo the addition reaction, okay? Because remember, as you can see here in yellow, it's more correct that we actually think of benzene having those electrons fully delocalized. They're not really found in 3 double bonds, all right? So we're going to use this sort of delocalized idea and have a look at the mechanism for what's called nitration. This is where a nitro group, NO2, replaces a hydrogen that would normally be found in benzene. There's the reaction conditions. You need to know that it requires nitric acid, concentrated sulfuric acid, and the whole thing has to be performed at about 50 degrees. Alright, so you'll need the conditions, and then if asked, you'll also have to be able to explain or describe the following mechanism. Okay. This occurs in 2 steps. The first is the formation of what's called the nitronium ion, and in order to do that, we need to make use of the relative strength of the acids. So of the strong acids, nitric acid is the weakest, and sulfuric acid is considerably stronger. What will happen here is the sulfuric acid will, which we'll represent here just as a single proton. All right, you'll see in a second, I'm going to change the color of that proton to red. It will force itself onto one of those oxygens in the nitric acid molecule. Okay, this is the slow step. So if you were asked to draw a potential energy diagram, this would be your rate determining step. This would be basically in common speak, this would be one of the bigger hump. This would be the bigger hill on the graph. All right, so here I'm just going to show where the sulfuric acid proton goes. All right, so you can see what's essentially going to happen here is that HOH is going to come off of the nitric acid molecule as water. Okay, so that'll release. Right, so here we are. This 2 equilibrium reaction. So as you can tell, this would be the first step is clearly the rate determining step. All right, this releases water and then what's called the nitronium ion. So it's a nitrogen atom that has 2 double bonds to oxygen atoms. So the nitronium ion will then readily react with the benzene molecule that is present. So, and this reaction is considerably faster than the equilibrium rate determining step. So once nitronium forms, that region of high electron density, okay, which we'll represent just as the ring, essentially attacks that positively charged nitrogen center. Right, so there's lots of electron density there, right? And this attacks that positively charged nitrogen center. This forms then a bond between the carbon atom, or one of the carbon atoms, which we'll just represent as the carbon 1 up here at the top of the ring. And what happens is that carbon now becomes 4-coordinate. Alright, and the positive charge is taken off of the nitrogen atom and brought into the ring. So that positive charge is now spread equally over the remaining 5 carbons of the ring. Right, we're not going to worry about exactly where it's located because, again, it's shared. This is why benzene is able to perform this substitution reaction, because rather than just a strictly addition reaction, because it can actually stabilize that positive charge and just replace a hydrogen, let's say in this case for the nitro group. So you can see what would happen here. The pair of electrons gets donated from the hydrogen back to the ring. The hydrogen gets reformed, the H plus gets reformed. You can see that it's a catalyst, and we end up with nitrobenzene.